There are two laws in magnetism. One is Biot-Savart's law and the other is Ampere's circuital law. The Biot-Savart's law is already being taught, and this law, Ampere's circuital law, is an alternate method of finding the magnetic field. Similarly, there are two laws in electrostatics. One is Coulomb's law and the Gauss law. Gauss law is an alternate method of finding electric field. There are some similarities between them. That is the reason I have taken it again for a discussion, the Gauss law. The Ampere circuital law is analogous to Gauss law. Ampere's circuital law of magnetism is analogous to Gauss law of electrostatics. Similarly, the Biot-Savart's law of magnetism is analogous to Coulomb's law of electrostatics. To understand the differences and the similarities, we shall understand the statement of the laws, that is Ampere's circuital law and the Gauss law. Let us understand the statement of this law. Here written, this equation is a mathematical statement of the law. To understand this mathematical statement, we do require a suitable geometry of drawings. This is a geometry we require. In this geometrical drawings, there is a straight conductor which is carrying current, amount of current is I. And as you know, the magnetic field around the conductor, there are concentric circles. There are concentric circles at every point on the conductor. The concentric circles are numerous at every point. I am taking in the diagram a point on the conductor. About this point, I am taking only one circular line, not all the concentric circles, only one circular line about this point. Look at that lines. This straight line explains, says electric current is flowing in this line, or it is the charges flowing along this line in this direction. And on the way along, it is on the way around it, this is circular line, represents the magnetic field and also the length of the line. Magnetic field and also length of the line. And let me take a point, any point on the circle. I am taking this point on the circle, this as a P, this point. At that point, two vectors are operating. What are those vectors? One is B. The magnetic field is a vector. here at this point, and also dl is a vector. What is dl? dl is a differential function. L stands for length of the line. dl means infinitesimal length. It is also called as element of length. This element of length also has a direction, and magnetic field also has a direction. The element of length at this point is a straight line because infinitesimally small dl, and the direction is tangent to the point, that is a straight line like this. So direction of dl is tangent to the point at this point. This is a line represents. So because direction is, this is the direction is indicated. So this direction of magnetic field in accordance with the palm rule, right hand palm rule, that is holding that thumb indicates direction of the current and the movement of the curling finger indicates direction of magnetic field. So that is why length is also in the same direction. The dl direction is straight line like this. And also what is the direction of the electric field? Where is magnetic field at this point? Direction is also known as a tangent to the point at this point. Tangent to the circle at this point. That is also a tangent, this line. This is a direction of the magnetic field at this point. A tangential line, this arrow mark, is the direction of the magnetic field at this point. And interestingly, this dl direction and b directions are in the same line, in the same direction. In other words, the angle of separation between the vectors is 0, theta is 0. So at this point, the magnetic field is given by Ampere's circuit law. What is that magnetic field? The magnetic field is a product of the vectors. What are those product of the vectors? These vectors are operating at this point. Product of the vectors means dot product of the vectors. What is dot product of the vectors? Dot product means that is this value into this value into cos theta. So what is theta means? Theta is the angle of separation between the two vectors. B is a vector, dl is a vector. Theta. So it is B into dl at this point. So the magnetic field at this point is B into dl. So on the way around the what is that circuit around this current carrying conductor, a circular line, there are infinite number of points. This is at one point. Why there are infinite number of points? Because you have taken the length as infinitesimally small, element of length dl. So we have infinite number of points, and the total, what is that? The total amount of magnetic field at all the points, or it is all along the line, it is the total magnetic field I want to calculate. For that calculation, there is one mathematical concept, that is mathematics is integration of the function at this point. is the total magnetic field. Total magnetic field over the entire line, indicating the magnetic field as well as length of the line. So this is the mathematical statement of the left hand side. And one more we have to understand. In the integral we have one symbol, that is that circle is there. What is the meaning of this circle? It is an integration over the entire line. This line is what is that? A closed loop. It is a circular loop. So this is a closed loop. Total integration over the closed line of loop. This integral sign represents total, and that is integral over the closed line of loop, entire line, this symbol. So this is known as left hand side of the Ampere circuit law, equals, in accordance with this statement, this exactly equals to mu naught into I. What is mu naught? The magnetic field constant, magnetic permeability, that is explained already. And what is I? I is the amount of current flowing through the conductor. Amount of electric current flowing through the conductor through the plane. What is the plane here? Plane is enclosed. Assume that this circular line in plane. Assume that there is a plane is enclosed in the circle, enclosed by the circle. That is, I is the current passing through the plane, enclosed by line of the loop. That is the meaning of I. I inside means through the plane, which is always enclosed by the line, loop of line. That is a product. This is total amount of electric field over the line of circle, that is equals to mu naught into I. It is the Ampere circuit law. That is the actual statement of the law. So this is the law I explained. Let us understand the Gauss law also. This is already being taught. I want to bring it to your attention again, just because as a reminder for a comparison, reminding it again. What is Gauss law? For Gauss law means, again, this is mathematical statement. This is a mathematical statement of the Gauss law. Mathematical statement of the Ampere circuit law. Look at the differences. Here, to understand this statement, mathematical statement, we need again the geometry. What is the geometry here? A geometry of diagram. This is a geometry of diagram is required to understand the statement, this statement. What is this geometry? The line is here circular. It is not circular line. It is a spherical sphere. The hollow spherical sphere enclosing some amount of charge, which may be plus or minus. The diagram. If the charge enclosed is plus, the electric field, you see that electric field is passing in all direction in straight line, the field lines. Passing in all direction, passing through at every point on the spherical surface in all directions. These lines are showing straight lines. If the charge is positive charge, that is the direction of the electric field. Electric field lines are passing through at every point on the spherical sphere all around. That is the indication. To understand this mathematical statement, we have to take a point on the sphere. At this point, here again two vectors are operating. The vectors are, one is electric field, electric field, here comes electric field, there comes magnetic field, and here area, that area you have taken differential form dA is the element of area. Element of area has also a direction. Electric field also direction. What would be the direction of the area, surface area? The surface area is what is that? Infinitesimal area. Infinitesimal is small amount of area. So at this point I am taking the infinitesimal area, that is direction. Let us understand the direction of dA is a vector. dA is a vector, E is a vector. They have directions. What are those directions? The direction of any surface is directional. What is the possible direction of any surface? Suppose this is a surface. The direction of surface is normal to the surface. What is normal to the surface? Any line perpendicular to this surface is normal. The direction of surface is along this line. That is the direction. So if I have taken dA surface here, the surface is dA, its direction is like this. And at this point, direction of electric field is also same line. Both lines are coinciding in the same direction at this point. So it means two vectors are operating at this point, and the direction of the vectors, the direction is angle of separation between the vector is theta, that is 0, and the vector, the magnitude of electric field is given by the same type of formula. What is that? Dot product of the two vectors. Dot product of the two vectors E and dA. Similarity, dot product of these vectors. Here element of length, magnetic field. Here element of area, electric field. And as you know, the dot product of the vector is this value. What is that? E into dA into cos theta. Theta means angle of separation between the vectors. I said the angle of separation theta equals 0, cos 0 equals 1. It is simply E into dA at this point. Since the surface area, the entire spherical surface area is there, there are infinite number of points. I have taken only one point. Why infinite number of points? The area I have taken is infinitesimally small. So you have to calculate electric field at all the points, or the electric field for the entire surface area, for the entire spherical surface. So we are using that mathematical concept. What is that? Same type. Integral of the function, integral of this vectors, vector product. And the integral sign as the similar, that is similar symbol here. What does the symbol represent? This circular symbol represents not circular line. It is what is that? Closed surface. This symbol, the closed line. A Suppose circular line. Here the closed surface. This represents the closed surface. It represents the closed line along which the magnetic field is existing. Here the closed surface, so about which magnetic field is existing. That's the meaning. So as you know, the product is the integral of this entire. It is integral over the closed surface area. It is same as electric flux, total electric flux through the entire, what is that surface? The surface is spherical surface. It is also called as total electric flux over the area, over the surface area. So this equals to Q divided by epsilon naught. Q means Q enclosed. N stands for enclosed. Only the charge enclosed in the surface. That is the magnitude. So whatever the amount of charge enclosed will decide the electric field at the surface. That is one. Divide by epsilon naught. What is epsilon naught? Epsilon naught is, that is a constant for electrical, what is our permittivity of the free space, electrical constant, your magnetic constant. Magnetic permeability, what is electrostat, electrical permeability, electrical permittivity. So difference I told you, it always comes in numerator, it comes in denominator. So 1 by epsilon into the amount of charge enclosed and mu naught into I. Look at the difference. The magnetic field over the entire line is depending on the amount of current passing through the plane enclosed by the line. And the electric field over the entire surface area, it is depends on what is that amount of charge enclosed, Q. Difference. Electric field depends on the amount of charge. Magnetic field depends on the amount of current in the conductor. The differences. So these are the similarities. Look at that. This Ampere's circuit law, Ampere's circular law is thus analogous to the Gauss law this way. So right hand side it depends on the current through the conductor, and right hand side depends on the amount of charge in the system. And the rest of the thing, either you have to calculate what is the amount of magnetic field at this point. I don't want entire magnetic field up there. To every point, we need to understand what is the field at a point in the space surrounding the conductor. So how do we eliminate or estimate the amount of electric field at this point? Use the same, what is the mathematical statement. You simplify the left hand side. How do you simplify? Take the left hand side of the statement. The left hand side of the statement is the integral of this. As you know, this dot product is this. Definition of dot product is this into cos theta. Theta is 0. So cos 0 equals 1. This becomes finally this one. And here, so b into dl. Integral of b into dl in these two functions, among these two functions, b is a constant. dl is of course variable for the length. Why b is constant? At this point, take any point in the circle. Reason, the magnitude of b depends on the r. What is r? Distance between the point here and this point. It remains same. So the r remains same, the magnitude of b remains same. It is always a constant at all points on the line. That is why this constant into we have integration finally. The integration of the dl is L. Integration of dl is L. L is, what is L? The total length of the circle. The total length of the circle is called as circumference of the circles, 2 pi r. B into 2 pi r. So B into 2 pi r is the total magnetic field over the entire line, and equals the right hand side. What is right hand side? The left hand side is this, equals the right hand side, mu naught into I. If this is the equation, then what is for B? B equals. So what does the B represent? B is the magnitude of B at this point, equals mu naught I divided by 2 pi r. 2 pi r. 2 pi r goes to denominator. So final expression we arrived at is B equals mu naught I divided by 2 pi r. Expression for magnetic field at this point. So this is how we arrived at this expression. The same expression we have got it in the previous class using Biot-Savart's law. Using Biot-Savart's law followed by mathematical derivation. It was a laborious process. So now it is the easiest way to find the magnetic field. This is the way. So this is how we can find the magnetic field by Ampere's circuital law. It is an alternate method to Biot-Savart's law. So again I am recalling this, reminding you of this calculation about just the similarities to comparison. For a comparison, simplification of LHS, the integral of this, apply the definition of the dot product of vector. This cos theta, this into this in cos theta, theta equals 0, cos 0 equals 1. Finally, it is integral of these two functions. And E again, look at that, among these two functions, electric field is a constant. This electric field, if you take it at any point on the, what is the spherical surface, it remains constant. Reason for that is the distance between the point at any surface, point at any space, any surface, and this point is always r. Distance between the point and this point, everywhere on the surface, is r. It depends only on the r. R remains constant because E also remains constant. So electric field is constant at all points. So finally we have integration of dA. Integration of dA is A. What is A? It is a surface area. What surface? Spherical surface area. Entire spherical surface area of the sphere. So spherical surface area of the sphere is given by the formula pi 4 pi r square. What is r? Radius of the sphere. 4 pi r square. This is left hand side of the equation. E into 4 pi r square, total electric flux of that surface. So this LHS equals, this is RHS. Simplify, E equals this goes to denominator, and final expression is 1 by 4 epsilon naught is K. We know that it is a Coulomb's constant. KQ divided by R square. So this is how we arrive at this equation. What is the equation? Equation for electric field at this point, or this geometry, is the easiest way to approach. This is also done. This was also derived somewhere in the previous class using Coulomb's law followed by derivation. It was a laborious process. So these are the differences or similarities between the laws in magnetism and laws in electrostatics. It is analogous to Gauss law, and Biot-Savart's law is analogous to Coulomb's law. So this is the one I have taken just for a comparison between the two. So this is about this. Let us continue with the next in the next hour. Thank you.